Sodium gates can be a bit tricky, so let's kind of illustrate that here, just to make sure we've got that correct. Okay, so we're looking at the voltage gated sodium channels. And specifically its events during an action potential. So we want to make a note here, some features of this channel. It's voltage sensitive. Meaning that it's going to open at -55. And it's going to close at +30. Okay. The second thing we want to point out here is that it has two gating mechanisms, or two gates associated. We've got the activation gate, which is voltage dependent only. And then we've got the inactivation gate, which is both voltage and time dependent. Okay, so let's look at the three states of this gate here. So we're going to start with the gate at rest. We know that this is -70 millivolts. And then we're going to look at the depolarizing state. Which is -55, that's the threshold value. And then we're going to look at what happens with repolarization. And the signal for that is +30 millivolts. So again, because this is a voltage sensitive channel, at -70, it's in its resting state. At +55, it's going to be in its depolarizing state. And then at that was -55, not +55. At +30, it's going to be in its repolarizing state. And so we're going to look at what that looks like here. So I'm just going to draw the three states of this gate, of this channel rather, and then look at the two gates that are attached here. So we've got at rest, the activation gates are closed. Okay. But the inactivation gate is open. So let's get another color here. Okay. So the activation gate is closed, but the inactivation gate is open. Okay. And so here we can say that the channel is closed, but capable of opening. So the channel is closed, but capable of opening. And that is because the activation gate is closed But very importantly, that inactivation gate is open. Remember, nothing can happen if that inactivation gate is not open. All right. Let's look at what happens at threshold. So we have a bunch of small graded potentials that get us to our threshold value, and then we're at -55. And so now we see the activation gates open. And the inactivation gates are also open at this time, but we'll talk about that 1 millisecond signal here. So activation gates open at -55, inactivation gate is already open, but now we have a 1 millisecond signal into effect. Okay, so we've got a 1 millisecond delay happening here that will then create this state after 1 millisecond. And so the channel in this state is said to be open. Let's make a note at the bottom here. So the channel is open. Right? No conditions because the activation gate is open. And the inactivation gate is also open. Alrighty. But after this very brief 1 millisecond, the channel will be in this third state. It's going to be in the repolarizing state where the activation gate is still open, but now the inactivation gate has closed. So our activation gate is still open here. But the inactivation gate has now closed. And that's because of the signal that was sent here. So now we close the inactivation gate. And so we can say here that the channel is now closed and incapable of opening. So in this state, the activation gate is open. But the inactivation gate is now closed. And the channel will remain in this position until the membrane potential gets back to -70. And then when it gets back to -70, the inactivation gate will open once again. All right. Now, this third state of the channel is really important. It coincides with what we call the absolute refractory period. And I'll talk more about what that is, but basically after we fire an action potential, there's a period where we cannot fire another action potential, even if the strongest of stimuli is initiated. There's a brief period where, because this inactivation gate is closed, it's not physically possible to fire another action potential. So the third state of the channel here coincides with the absolute refractory period. Okay, so until the membrane potential returns to -70, we cannot fire another action potential, and that's what's meant by the absolute refractory period. All right, so let me just go over this here once again. So we've got 3 states of our channel. We start off at rest with the activation gate closed, but the inactivation gate is open, and that's the most important condition for being able or capable of opening. Let's say it opens up, we get to -55, right? The activation gate now opens. The inactivation gate is already opened, but that 1 millisecond signal is sent to close it after that time has expired. So here the activation gate is open, the inactivation gate is open, sodium is actively rushing into the cell, and that's what's creating this upward stroke, and that's what gets us from -55 all the way up to +30. At +30, that 1 millisecond delay is going to close the inactivation gate. And here, the activation gate is open. So the channel is closed, but it's completely incapable of being open until we get back to rest, okay? And again, this coincides with that refractory period where we cannot fire another action potential without going back to that resting membrane potential. All right. Let me pause here for a bit and see what questions you have. Okay, any questions about the gating mechanism here? Okay, so really good question here. Can something still happen if the activation gate is closed, but the inactivation gate is open? So that's the state of the channel at rest, and something can absolutely happen. If we have the right stimuli that brings us to threshold, we can absolutely open up the activation gate and begin that depolarizing event. So activation gate closed, inactivation gate open is the state of the channel at rest. And so this is where the channel is open, it's capable, not open, it's closed, but it's capable of opening. So we can kind of think of it being open and ready for if a threshold stimuli comes about.